So, in the last lecture we talked about the design for testability technique. So, one method we looked at, namely the scan path. Now, in the current lecture we shall be looking at some of the standardization effort in this regard. See, scan path is a concept, but various manufacturers can implement scan paths in different ways. Now, imagine a scenario that I am a system integrator or an assembler. I have manufactured a motherboard on which I have put, let us say, 10 different ICs which may be manufactured by different companies. Now, once I put the chips in the ICs, now my trouble starts. How do I test my board? Each of these chips is a VLSI chip, those are complex containing millions and billions of transistors. So, how do I test the chip once they are soldered on the printed circuit board? There has to be a solution there, and again, unless the companies agree among themselves on some standards, it is very difficult, almost impossible to come up with a feasible way to do this. Now, fortunately, such a standard exists called the boundary scan standard, which we shall be looking at briefly in this lecture. So, this is actually one of the standards like I was talking about. So, you know how a manufactured chip can be tested. We looked at several methods, test generation, DFT and so on. As I said, different manufacturers may use different methods for testing. So, there is no standardization, or there was no standardization. So, when several chips are assembled on a board, so how do I test the individual chips while they are residing on the board? So, what was done is that there was an action group called Joint Test Action Group, JTAG, this is the short form of it, was formed, which was comprised of several of the leading semiconductor manufacturers and academicians, and finally a standard called IEEE 1149.1, which is sometimes also called boundary scan standard, which emerged. Now, it became so popular that nowadays most of the people call them as the JTAG standard, JTAG port, JTAG standard. That is a noun which is being used by many designers and users today. It has become so popular. Okay. So, some of the features of this boundary scan technique is as follows. Here we apply tests as some kind of instructions. Like, let me show you the overall perspective. Like, I have a printed circuit board, I have a board. So, there are several chips which are residing on the board. Let us say there are several chips, and on the edge of the board I have some kind of a connector through which I can feed some signals, right. Now, my question is, how do I test the individual chips? Now, the idea is something like this. So, we tell the manufacturers that when you manufacture the chip, you also manufacture something else. This is called something called a wrapper. I will just talk about it shortly. So, I manufacture something else, means around each of the circuitry of the chip. Okay. So, once I do it, my advantage is that I can connect these chips together for testing. Let us say this is the direction, let us say. There can be other signals also, I am showing just one signal. Now, how do I do test? First, I must tell from outside that what kind of test I want to do. That is done using something called a test instruction. This is like I am having a very simple processor in this wrapper, where I am serially feeding in an instruction. This wrapper is decoding what kind of instruction it is, and it is taking appropriate actions. Now, these boxes that I have showed, dotted boxes, these are IEEE 1149.1 wrappers. Now, these wrappers allow interoperability in terms of test communication. Like a test instruction I am feeding to the first chip, if this chip finds that this instruction is not for me, it is for the next one. So, it will simply bypass or forward it to the next chip. This will again check, if it is not for this, it will bypass or forward it to the next chip. Like that it goes on. Okay. Fine. So, this standard allows test instruction and data to be serially fed into a particular chip on the board. It also allows reading out of the outputs or the test results. Some of the chips may be having a BIST or a built-in self-test mechanism that we will talk about later inside. This means the chip can test itself. That can also be included as an instruction, and the standard is hierarchical. So, you can work it at the chip level, PCB level, and also at the system level where there are multiple such boards connected. So, the serial output from one board can go into the serial output of the next board. Like that you can change. This is a hierarchical kind of a standard, not only meant for chips on a board. On a single chip you can do it, multiple chips on a board you can do it, multiple boards also you can do it. Okay. So, here you test not only the chips, the circuitry inside, but also you can test the interconnections, because when we have several chips on a board, not only the correctness of the chips, but also whether the interconnections are correct, there is a break or short circuit, this kind of things also have to be tested, right. So, JTAG allows all these things to be done. So, as I had said, the basic idea is to have a test wrapper for every chip or component that is manufactured. In fact, the EDA tools using which you design the chips, they have a single instruction, an instruction to create the wrapper. Once you are complete with the design, you can create the wrapper with it using a single command. So, the wrapper will be automatically generated and the corresponding netlist done. So, this I shall show how it is done. So, that in the test wrapper, corresponding to every input or output pin, you have something called a boundary scan cell. Now, in addition you can have some registers and some extra pins for testing, for interfacing with the wrapper, some serial input, serial output, something like test control and so on. And there are some test instructions, as I said, which are also fed serially. There is a particular format in which you can feed the instructions. Now, this diagram shows how the test wrapper looks like. You see, this blue rectangle in the middle, this is my actual circuit which was supposed to be there in the chip. So, without all these things, this would be my whole chip, but now I have put so many other things also. So, what I have done, these small rectangular boxes here, these are the so called boundary scan cells. So, I have put one such cell means alongside every input or output pin. Now, each of the boundary scan cell, as you can see, there are 4 connections, one from bottom, top, left and right. So, they are connected in certain way, like from the external pins of the chip, when a signal comes, the signal can be sent to this internal logic from left to right connection. But sometimes when you want to test something, you can configure them as a shift register mode. From here you can shift the data serially along this path, again you can serially, you can send the data out from this test data out or TDO. TDI stands for test data in, test data out. Now, in addition, there are some registers like an instruction register which can hold the test instruction that is being loaded. there is a bypass register which can help you to skip this chip and go to the next chip if required, and there can be other miscellaneous registers, multiplexers and connections. And these special signals, 5 of them are shown. The one marked star means this is optional, but other 4 are mandatory signals. They are controlled by something called a tap controller. Tap stands for test access port. These signals constitute the test access port. Like here, if you come back to this diagram once more I have shown. So, here I said that at the edge of the PCB I am sending some signals. So, actually these will be the test access port signals. So, I need 4 or 5 of the signals from here. Okay? All right. So, this is how the wrapper works. So, once you design a chip, the circuit for a chip, you give a command, the rest remaining part can be automatically included with it, and your whole integrated chip, which is now set to be 1149.1 compliant, can become ready. Okay. Now, the content of the wrapper, as I said, so that is called a test access port. 5 control signals are there, one of them is optional. Test data in, this is somewhat very similar to the scan in of the scan chain method. Test data out is similar to scan out. Test mode select is similar to test control and test clock. So, you see that the concepts which are used here are very similar to the scan path concept that we had seen just earlier. And this tap controller is again a sequential circuit, a finite state machine, and there are 16 states actually, I am not going into detail. So, it is not a very complex controller, quite simple one. Now, among the special registers, these 3 registers are mandatory. You must have the boundary scan registers alongside the input and output pins. You need to have a bypass register in case you want to skip a chip. You need to have an instruction register to store the test instruction. Now, in addition, you can have some other registers which are very specific to a design, like you can use a register where you store the ID of a device, so that from outside you can read out the ID and check the identity of the device, which device it is. Okay. Similarly, there are some registers which are very specific to design specific. Just let me tell you in this context that for those of you who are familiar with FPGA boards and FPGA kits, so you may have seen that the way you do programming on the FPGA kit, typically from a desktop or a laptop, you connect a port that is called a JTAG port. Now, that JTAG and this JTAG is the same. That JTAG port was used primarily for testing, but nowadays that same port is used for downloading the configuration data for FPGAs, that serially through the TDI input, those are getting shifted inside the chip. Okay. So, the same port is used for other purposes also. So, the basic operation is that we feed the instruction serially into the instruction register. The selected test circuitry will get configured accordingly depending on the instruction which has been fed in. So, the multiplexers controls will be selected and so on. So, whatever is intended will get executed, and after completion the test results will be shifted out through the TDO pin. And while this is being done, new test data can be shifted on TDI, just like scan out and scan in was overlapped in the scan path method. You can do the same thing here also. Fine. Now, the boundary scan cell, it looks like this. So, again in a schematic sense, if you look at the boundary scan cell as a black box, boundary scan cell. So, from the left side you have a signal, let us call it in, on the right side there is a signal called out. So, from bottom there can be a signal S in, and from top there can be a signal S out. this is the schematic. So, we can move a data from left to right or from bottom to top. Now, let us see what is there inside. There are 2 flip flops, there are 2 multiplexers. So, when the input data is fed to a chip, I want to send it directly to the circuitry inside. So, the remaining part is bypassed, in will go straight to out. So, this mode control, if it is 0, then the 0 will be selected, so it will go out. So, for going from S in to S out, the path followed will be this. From S in, you select the lower input of the multiplexer, it will be stored in the first flip flop, and the output of this flip flop will go out here. There is also a mode in which from S in you can move it to out. So, from bottom to right there also is a path, but there are 2 flip flops as you can see. One flip flop is used for shifting, other flip flop is used for actually capturing, because see, while this shifting is going on, you should ensure sometimes that data here is not changing. So, you can copy the data here, retain this, and during that time you can shift something here. So, some changes are going on in this flip flop, but the second flip flop and here this out will not change. Okay, so, roughly this is how the boundary scan cell looks like. Now, basically there are 4 modes of operation. Normal mode, I set mode equal to 0. So, in goes to out, just as I said mode is 0, in goes to out. Second one, I say this as a scan mode. Here shift DR is set to 1 and clock DR is activated. So, let us see, shift DR is set to 1 means S in is selected and clock DR is activated, which means S in gets stored here. So, I am creating a chain of flip flops. There are several such boundary scan cells connected one after the other, okay, one after the other they are connected. So, this S in will go to S out, that will go to the S in of the next one, S out. So, they are chained as a shift register, just like in this scan path design, okay, same way. So, this is called scan mode, and in the capture mode shift DR equal to 0 and clock DR. Shift DR equal to 0 means in is selected and clock, that means the input I am storing here. So, here I am not storing the value of S in, but whatever is coming from the input of the pin, I am capturing it and storing it here. This is the so called capture mode. So, in goes to QA and out can be driven by either in or QB. Output depending on the mode, it can be either from here or from here, but the important thing is that in is getting captured here. Okay. There is another mode called update, where QA to out, the value of QA can go to out, this is also there, fine. Now, here we shall be showing you 3 of the important test modes of the boundary scan. There are other modes also, X test, bypass and in test. Now, the X test mode is used to test the interconnections between the chips. Bypass mode is used to skip one chip and go to the next one, and in test is used to test a particular chip, that means the internal logic. Let us look at the basic concepts one by one. Well, X test diagrammatically it looks like this, so the diagram may be too small for you to read, but I will just explain the steps. Suppose there are 2 chips on the board, one is this and the other chip is this. So, TDI, TDO. So, what I do, I activate shift DR. So, what will happen if shift DR is activated? Let us look at this diagram once more. If shift DR is activated, then S in gets inside here, right. So, that same thing happens. So, it is actually the scan mode, shift DR equal to 1 means I am looking at the scan mode. So, in the first chip we are in the scan mode, all the boundary scan flip flops they are in the scan mode. So, what I do now, So, after setting it in the shift DR mode, we serially apply bits to TDI. So, these bits will be serially shifted through the shift register, okay, and they will reach these scan cells. Suppose I want to test one of the interconnections here. So, I wait till these bits reach this flip flop, this boundary scan. So, I apply so many clocks. So, after it is done, I do an update on DR. Update means the data was there here on this flip flop, it will get shifted to the next flip flop and made available on out, which means, so whatever I was shifting, now the data will be available on the output pin, and captured DR means whatever is coming on this line, this is for chip 2. Chip 2 will be capturing it in the first flip flop. So, now you see what you are doing. What we are saying is that whatever bit was shifted here, I am moving that bit to the second chip, I am capturing it here. Okay. Then after capturing, I am configuring the chip 2 in the shift mode again scan mode, and again I am applying clock, so that this bit which was captured will get serially shifted out through the TDO pin. So, if this interconnection was faulty, then what bit pattern I am shifting in and the bit pattern that is coming out will be different. So, by checking this, by checking the validity of these bit patterns, I can verify whether this interconnection is working correctly or not. The same thing can be done for multiple interconnections together. So, I can just capture multiple such patterns together and shift in together. Okay. This is X test mode. Then comes the bypass mode. Bypass mode is fairly simple. There is a bypass register I mentioned. Now, bypass register is just a single flip flop, it is a 1-bit register. In the bypass mode, whatever I am feeding in TDI, it does not go to the boundary scan cells. It directly comes to this 1-bit flip flop, and after a 1-bit delay, when a clock comes, it comes to TDO. So, whatever bits you are shifting here, this particular chip will be bypassing that, and it will be straight away sending them to TDO. So, it can go to the next chip. Okay. Bypass is used to skip a particular chip. And lastly, let us look at a test mode using which we can test the internal logic. So, here the concept is quite similar as compared to X test, because in the first step we configure the chip in the shift DR mode, so that whatever we feed through TDI will get shifted. But you see, we shift it here, I am showing up to here, but it will get shifted up to a point, so that all the inputs to the internal logic are applied. So, once these are applied, you go to the update DR mode, means whatever there in the first flip flop will get saved in the second flip flop, and now they will be available as input to the internal logic. So, now the internal logic will do some computation based on the applied input, and after the computation is done, you activate the capture DR signal. So, the output will get captured on the first flip flop of the boundary cells. Then again you configure in the shift DR mode and shift them out serially. So, this is exactly similar to the scan path approach for sequential circuit testing. We scan in our test data like this, we scan out like this. Now, here again, so it is not necessary that we will be scanning in all of them, maybe a part of them we are scanning in. And let me also look at one thing, let me go back to that wrapper diagram. Here you see here that in addition to the boundary scan cells, there can be also a scan in and scan out pin for this internal logic. So, there is also a facility, whatever data you are feeding, that can go directly into your scan in of this internal logic, and scan out whatever is coming out, that can also go out and be available over TDO. Okay. So, this mode is also there. So, it is not that you are saying that internally you cannot use any scan path, that also you can use. Okay. So, it is like a combination. Okay. So, let us go ahead. So, you see that here using all these test modes you are able to get some kind of a board level infrastructure where you can test the individual chips on the board, you can even test the interconnections between the boards. So, to summarize, the JTAG 1149.1 standard has been quite successful in the sense that most of the chips that we see today that are being used, they have this standard built in. And just as I said, they are used for other applications as well, which has nothing to do with testing. Like I said, the downloading of the programming bit files on the FPGA boards. Now, this JTAG 1149.1 standard, this has been extended also in a number of different ways. Like there has been an analog boundary scan version, it is standard which allows also analog signals to be fed to a circuit. This can be used to test the mixed signal kind of chips, where there are both digital and analog components involved. And another thing, you know that today we are moving, or means we have already moved, you can say, so it is not today, towards something called system on chip designs. Like earlier we are talking about chips on the boards, now the VLSI chips have become much more dense. Now, all those chips on the boards can be squeezed into a single chip today. So, whatever was a separate chip earlier will be something called a core inside my chip now. My chip will be consisting of multiple cores. So, whatever requirement we had for board level testing, we have now the same kind of requirement for a core level testing, but inside a chip. Multiple cores, some of the cores might have been taken from some other designers, it may not be my design at all. I want to test the integration of the cores. Okay. So, this is a standard called P1500, this is meant for system on chip. This is also quite popular for the present day system on chip designs. This is also an IEEE standard, so which are also been used. So, here as I said that chips on boards have been moved to multiple cores on a chip, and we use very similar concepts. So, I think with this we come to the end of this lecture. So, in the next couple of lectures we shall be looking at something called built-in self-test, like a technique where a chip can test itself. That is the best thing which you can think of, right? But there are constraints that we will see. But for today I think that is all. Thank you.